At the end of this video, you should be able to explain the relationship between the motion of an object and the net external force acting on the object, determine the net external force on an object, and calculate the force required to bring an object into equilibrium. Chapter 4, Section 2, Newton's first law, Inertia. A hovercraft, such as the one in Figure 2-1 or on the screen now, glides along the surface of the water on a cushion of air. A common misconception is that an object on which no force is acting will always be at rest. This situation is not always the case. If the hovercraft shown on the screen here is moving at a constant velocity, then no net force is acting on it. To see why this is the case, consider how a block will slide on different surfaces. First, imagine a block on a deep, thick carpet. If you apply a force by pushing the block will begin sliding, but soon after you remove the force, the block will come to rest. Next, imagine pushing the same block across a smooth, waxed floor. When you push with the same force, the block will slide much farther before coming to rest. In fact, a block sliding on a perfectly smooth horizontal surface will slide forever in the absence of an applied force. In the 1630s, Galileo concluded correctly that it is an object's nature to maintain its state of motion or rest. Note that an object on which no force is acting is not necessarily at rest. An object could also be moving with a constant velocity. This concept was further developed by Newton in 1687 and has come to be known as Newton's first law of motion. Newton's first law. An object at rest remains at rest, and an object in motion continues in motion with constant velocity, that is, constant speed in a straight line, unless the object experiences a net external force. Inertia is the tendency of an object not to accelerate. Newton's first law is often referred to as the law of inertia because it states that in the absence of a net force, a body will preserve its state of motion. In other words, Newton's first law says that when a net external force on an object is zero, the object's acceleration, or the change in the object's velocity, is also zero. The sum of forces acting on an object is the net force. Consider a car traveling at a constant velocity. Newton's first law tells us that the net external force on the car must be equal to zero. However, the image on the screen now shows that many forces act on a car in motion. The vector F, standing for force, F forward, represents the forward force of the road on the tires. The vector F resistance, which acts in the opposite direction, is due partly to the friction between the road surface and the tires, and is due partly to air resistance. The vector F gravity represents the downward gravitational force on the car, and the vector F ground on car represents the upward force that the road exerts on the car. To understand how a car under the influence of so many forces can maintain a constant velocity, you must understand the distinction between external force and net external force. An external force is a single force that acts on an object as a result of the interaction between the object and its environment. All four forces on the screen here are external forces acting on the car. The net force is the vector sum of all forces acting on the object. When many forces act on an object, it may move in a particular direction with a particular velocity and acceleration. The net force is the force that, acting alone, produces exactly the same change in motion. When all external forces acting on an object are known, the net force can be found by using the methods of finding resulting vectors. Although four forces are acting on the car on the screen here, the car will maintain a constant velocity if the vector sum of these forces is in fact equal to zero. Mass is a measure of inertia. Imagine a basketball and a bowling ball at rest side by side on the ground. Newton's first law states that both balls remain at rest as long as there is no net external force acting on them. Now imagine supplying a net force by pushing each ball. If the two are pushed with equal force, the basketball will accelerate more than the bowling ball. The bowling ball experiences a smaller acceleration because it has more inertia than the basketball. As the example with the bowling ball and the basketball shows, the inertia of an object is proportional to the object's mass. The greater the mass of a body, the less the body accelerates under an applied force. Similarly, a light object undergoes a larger acceleration than does a heavy object under the same force. Therefore, mass, which is a measure of the amount of matter in an object, is also a measure of the inertia of an object.
To illustrate inertia, let's look at a kickball and a bowling ball. The kickball is hollow and has little mass. The bowling ball has a lot of mass. Let's apply a force to the kickball. The kickball has little inertia because of its small mass, so a force will cause it to accelerate rapidly. The bowling ball is very massive. Its large inertia causes it to resist changes in motion.
Equilibrium. Objects that are either at rest or moving with constant velocity are said to be in equilibrium. Newton's first law describes objects in equilibrium, whether they are at rest or moving with a constant velocity. Newton's first law states one condition that must be true for equilibrium. The net force acting on a body in equilibrium must be equal to 0. The net force on the fishing bob in the figure A on the screen now is equal to 0 because the bob is at rest. Imagine that a fish bites the bait as is shown in figure B. Because the net force is acting on the line, the bob accelerates toward the hooked fish. Now consider a different scenario. Suppose that at the instant the fish begins pulling on the line, the person reacts by applying force to the bob that is equal and opposite to the force exerted by the fish. In this case, the net force on the bob remains 0, as is shown in figure C on the screen. And the bob remains at rest. In this example, the bob is at rest while in equilibrium, but an object can also be in equilibrium while moving at a constant velocity. An object is in equilibrium when the vector sum of the forces acting on the object is equal to 0. To determine whether a body is in equilibrium, find the net force, as is shown in sample problem B in this section. If the net force is 0, the body is in equilibrium. If there is a net force, a second force equal and opposite to this net force will put the body into equilibrium. At this point, you should be able to explain the relationship between the motion of an object and the net external force acting on the object, determine the net external force of an object, and calculate the force required to bring an object into equilibrium.